You know, it's all been very exciting for me. This whole year
Yes?
has been just insanely exciting. It's a wonderful thing, but you know, it's really just the tip of the iceberg.
Really? Just the tip, huh?
Yes, because I'm also into various other things. A lot of people don't know this, but I'm an expert in motivational hypnosis.
See, again,
Proof positive that aliens are moving and living among us. I'm sorry, Jay. I'm sorry.
I could see how that would affect your Christmas.
I made that whole thing up.
What?
I'm sorry. I guess I just wanted to seem interesting. I guess there's a real danger of that on this show.
There's a pressure.
Well, yeah,
yes.
people come out and they've run out of anecdotes, you know,
Yeah.
and they just start making stuff up.
Yeah.
Like that Neil Armstrong guy. Have you seen him on the talk shows?
Neil Armstrong, you mean the first man to walk on the moon?
Talk about a fish story.
Yeah.
Man, and they're buying it.
Oh, yeah. Now, you seem to be in pretty good shape physically. You work out all the time?
Oh,
You
I'm
look...
totally working out.
Yeah?
What I mean by that it's an illusion is that one would eventually like to know where it comes from, an explanation. Up to now we have, well, descriptions. I mean, Newton, of course, is the one famous for first writing down a theory of gravity. He could describe why apples fall and why the moon goes around the Earth using the same basic equation for gravity. But he described it. He had to assume that gravity was there. So not very happy with the fact that he should just, well, assume that these things, these objects, attract each other and without even anything in between. So if there are two masses in empty space, there's no nothing that really happens between them, but still they're attracting each other. And he thought that was kind of mysterious and that it was something he would have liked to explain in a better way.
Usually in science, if we're off by a factor of 2 or a factor of 10, we call that a problem. We say something's wrong with the theory. We're off by a factor of 10. However, in cosmology, we're off by a factor of 10 to the 120. That is 1 with 120 zeros after it. This is the largest mismatch between theory and experiment in the history of science.
If the sun is P and gravity is H, it makes a f. No, 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 no. The theory of relativity has escaped me. Why can't I get it? Why? Oh, this better be important. I'm thinking about black holes.
So later came Einstein, and Einstein, with his theory of relativity, eventually realized that also gravity has to be described in a different way. And it took him quite some years, but then eventually he wrote down a theory where he thought about space and time together. And then his explanation of what gravity would be is that there's masses which curve space and time. And then the motion of planets and of the Earth around the moon, or the moon around the Earth, is then described by thinking about moving in this curved space-time and how then objects are well, making their orbits. And the reason they go around then in circles is that that space and time itself is curved, in the sense that things don't move in straight lines anymore, they go around. So that was his explanation, but he had to write down an equation for it, which again assumed that gravity is there, because he basically wrote down that the matter curves the space-time.
That is 1 with 120 zeros after it. This is the largest mismatch between theory and experiment in the history of science.
My paper is try to start from a well, from a point of view where you don't assume gravity to be there. You would like to explain it by seeing how you can derive it from a more microscopic set of equations where gravity itself is not assumed, but then just follows from a certain logical reasoning. If you think about particles, very tiny particles, then it turns out that things like positions and velocities are not very precisely defined. You have to take into account the fact that there's an uncertainty in when we look at something. We may influence the measurement, but we may also there's a fundamental limit on how precise you can understand the position or the velocity of a particle. They cannot be not both described infinitely precise. So taking gravity into account then gives us a bit of a problem, because then we have to talk about space-time, and then these quantum uncertainties gives us another way of looking at space-time at the short distances. So this led to problems, and string theory is another way of also looking at gravity and quantum mechanics, which I've been working on quite a bit. So people have studied the problem of quantum mechanics and gravity from various perspectives, from string theory, but also by thinking, for instance, about black holes, what happens with black holes. And I've taken some of the things we've learned about it and seen that there is some explanation of maybe where gravity then comes from those new way of thinking about quantum mechanics and gravity together. So if you then start trying to explain where it comes from, it has to do with the fact that there's, at a microscopic scale, a certain information about how you describe this, which we don't see ourselves. We forget about that. And it turns out that if you take that into account in some appropriate way, that you can understand where gravity comes from. The theory that Einstein wrote down, when you apply it, for instance, to these black holes, you see that it starts resembling things that we call thermodynamics. That's a theory that describes how gases move when they give them a temperature, or when there is pressure, and you well, you can apply it in very many situations, but it's some way in which we describe how things happen at fairly large scales, in terms of not looking at the individual motion of the atoms and molecules, but by just thinking about these objects like temperature, pressure, and so on, which are what I call microscopic quantities. I mean, the temperature is something that is just an average of all of the motions, or the little collisions of atoms. Say, for instance, on my skin, if I think about what temperature I feel, it says something about the average energy that each of the molecules in the air is carrying. So temperature is not really a microscopic thing I can define. And so gravity is somewhat like that, in the sense that the equations that we currently use to describe gravity are basically obtained from averaging, or at least describing things at a much tinier scale, and then forgetting about certain details. So temperature, for instance, also forgets about how all of the individual molecules are moving. We don't have to keep track of that, but still we can describe quite well how gases move when we just talk about pressure and temperature, and even differences in pressure, for instance. Then if you have one room with one pressure and another room with lower pressure, you simply know that the gas will flow from one to the other. And these kind of differences is then necessary to get things moving. It's fun to think about things like gravity and even, well, what I had in my paper, things like even the laws of Newton, because they do play a role in one's everyday life. But it's surprising that when I go and walk out the door and something like that, it's not like I immediately sort of think about these things in a different way. But for me, I think it's more important eventually what will be the implications for understanding not just gravity, but also what's happening in the universe. I mean, the gravity equations of Einstein are also used in describing the expansion of the universe. The Big Bang theory are all based on these same equations. What I hope is that the ideas that we are now starting to develop for gravity can eventually sort of lead to possibly somewhat better or even more refined way of thinking about the early universe. And I think that will influence a little bit more my thinking than, I think as human beings we like to know where we come from and how the universe sort of developed into what it's now. And there I think eventually this will have some impact.
And now to measure the speed of light. Boy, that's quick. Oh!
Hello! So how about it, kid? Want some cookies?
No cookies!
Where does gravity fit in the electric universe? Contrary to a somewhat common misperception, the electric universe does not deny gravity's existence, nor its role in the cosmos and our own world. Rather, the electric universe theory, as proposed by physicist Wal Thornhill, suggests that the fundamental mysteries of gravity may be explained by the electrical structure of matter. In his 2008 article, Electric Gravity in an Electric Universe, Thornhill asks, when we apply force to a body, how is that force transferred to overcome inertia? The answer is electrically, by the repulsion between the outer electrons in the atoms closest to the points of contact. The equivalence of inertial and gravitational mass strongly suggests that the force of gravity is a manifestation of the electric force. Today, Bishop Nicholas Sykes further elaborates the query he first posed in his previous episode. What is the speed of gravity? And he elaborates the explanations for gravity that the electric universe proposes.
My last Space News video about the light-exceeding speed of gravity, titled What is the Speed of Gravity?, provoked some reactions. Someone wondered if I had never heard that gravity was not a force but a bending of the fabric of space-time. Another argued that gravity did not need explanation because it was something that was just there. Einstein's proposition that nothing can travel faster than light has become so entrenched that even some of us, identifying with the EU model as a whole, find it difficult to give fair consideration to the claim that gravity operating as a real force requiring a real explanation necessitates a real transmission far greater than the speed of light. Yet even if we are only at the beginning of providing such an explanation, it is important for the integrity of the EU model to adhere always to a simple force-based model for gravity, because gravity does, when all is said and done, manifest itself to our senses as a force. The electric universe model is constructed with explanations that invariably exclude just their formulations, which are, in effect, widely used agreements to discard the need for rational explanation. As a result of such agreements, the scientific landscape is littered with such follies as black holes, dark matter, dark energy, multiverses, and magnetic reconnection, all of them being just their formulations without rational explanation, designed to plug the holes in popular science theory with the unexplainable. Sir Isaac Newton understood that he was unable to formulate an explanation for gravitational attractions, even while he described the behavior mathematically of bodies under gravitational influence over vast distances with astounding accuracy. He speculated on gravity's cause, but decided to leave that issue to a future generation, who might bring better tools than his to master the task. Our own generation does indeed have better tools than his, but we have become distracted from the task he and others bequeathed to us by a multitude of follies. These consist of the extraordinary plethora of the just there formulations that prevent us from accomplishing what Newton and others bequeathed to a future age. If one reads the book Relativity by Albert Einstein, published, for example, in 2004 by the Folio Society, one will see that he develops the concept of light, or electromagnetic radiation, being the fastest possible messenger merely by assuming that since nothing was observed to go faster than light, then there is no credibility to the idea that anything could go any faster than light. In chapters 7, 8, and 9, for instance, he assumes that information from two simultaneous flashes of lightning could never, by principle, reach an observer any faster than light speed in a vacuum. From that simple idea, the whole theory of relativity was developed, starting with the deduction that two simultaneous events in one frame of reference might not be simultaneous in a different frame of reference. The theory of relativity as conceived by Einstein depended therefore entirely on the idea that one could never make deductions about space and time that might ultimately rest upon anything going faster than the speed of light. It is therefore illogical to assert, without any other reason for doing so than the theory of relativity itself, that nothing can go faster than the speed of light. To make such an assertion would be to engage in a tautology, i.e. circular reasoning, because the theory of relativity is founded upon that assertion in the first place. Only if the theory were independently and incontrovertibly verified by observation or experiments might this be reasonable, and such is often assumed to be the case, as Einstein himself hoped that it would be. But so far as I am aware, there is not a single case of this theory's verification that may not reasonably be disputed. Under these circumstances, therefore, it is entirely scientific to consider the possibility that there may well be something observable or reasonably deduced traveling at a speed faster than light. As has already been indicated in my videos, the motion of the planets in the solar system requires that the force of gravity between the Sun and its planets, assuming as we must that this is a real force and not a mental construction of some kind, must be transmitted between them at a speed many orders of magnitude faster than the speed of light. And the physicist Wal Thornhill shows also that such speeds of force transmission are just as necessary within what we call the fundamental particles of matter for the stability of those subatomic structures as it is for the stability of stellar planetary systems. Indeed, by such concepts, the physical foundation of the mathematical structures of quantum mechanics may yet be revealed and made clear in a way similar perhaps to the clarification of the physical foundation to Sir Isaac Newton's mathematical principles of gravitational action, that great task that he and others bequeathed to generations yet to come. In such manner, the electric universe model holds out a great promise, the promise of a physics and a cosmology that rest upon a secure foundation to replace what is taught in our prestigious schools, the current model, which, as Einstein himself discerned, relies upon two foundations, the theory of relativity and quantum mechanics, that are themselves mutually irreconcilable.
No, this is a you. We're just plain old us.
Why won't you leave me alone?
Boy, have we got a deal for you. For a limited time only. When you buy our cookies, we'll throw in the amazing Acme Pocket Fisherman. The Pocket Fisherman comes complete with fishing pole, tackle box, and potty. He may be small, but he eats.
But wait, there's more. You'll also get the amazing Acme Hair Magnet. A unique solution to fine limp hair.
Smile. You didn't smile. To get the cookies, Pocket Fisherman, and Hair Magnet, here's how to order.
Hi, I'm Dot, an operator here at Acme. Order now, and we'll also throw in Unexplained Mysteries of Fudge. Call now.
I don't think he can take much more, Captain. He's about to blow. I guess you really don't want any cookies, huh?
How can I eat cookies when the theory of relativity has escaped me? It's all wrong. All wrong. I am a failure. Einstein is a dummy. Stupid Einstein, dummy boy.
Hey, Einstein! Whenever we're feeling blue, here's what we always do. When your face is long, sing the Acme song, you'll feel so fresh and new. There's the A that's first, there's a C that's next, there's an M, you're almost done. There's the E, it's last, now spell it out, A-C-M-E, that's fun.
No, backwards! There's the E that's last, there's the M, it's next, there's C, you're almost done. There's the A, it's first, what's first is last, E-M-C-A, we're done.
Pretty good, Waggle, but your A always looks like a 2.
That's it. That's it. The theory of relativity. E equals mc squared. Energy equals mass times the speed of light squared. You kids is geniuses. E equals mc squared.
The Nobel Prize in Physics goes to Albert Einstein and the Warner Brothers.
And the Warner sister.
Hey, it's no merit badge, but it'll do.
James Lane, what do you want to do tonight?
The same thing we do every night, Pinky. Try to take over the world.